Okay, so continuing from last time, so essentially what's going on? Uh, we can finally wrap around some more features when the trajectory settles on the Lorenz attractor or the strange attractor. By that I mean these wings of the butterfly. Uh, so as we said, this is a fractal. It's called the strange attractor, and its dimension is between 2 and 3. Its dimension is about 2.05. Uh, of course, the amazing geometric properties of strange attractors is a whole new subject. Maybe some of you might be doing your project on that. Uh, so, one of the hallmarks of the motion on the strange attractor is the following. It's what is central to chaos: exponential sensitivity to initial conditions, or an exponential divergence of nearby trajectories. So, two trajectories, so let's say we already saw that in over this plot. Two trajectories, red and blue, can start very close to each other, but after some times one might be on this butterfly wing, other might be on this wing. Or if I start with a blob of initial conditions, then that blob of initial condition, let's say this was my 3D attractor, I start with a blob of initial conditions, and now this color is going to spread all over. So all trajectories emanating from here, they might be at different locations. Each of these trajectories might be at a different location at uh, different point of time, and this blob is going to smear over the entire attractor. That's the idea. So the blob of initial conditions eventually spreads over the whole attractor. So this actually makes, what are the consequences? This makes long-term predictions very difficult or impossible. Any trajectory starting here can be anywhere. How do you predict such a thing? Uh, so how does one quantify this sensitivity? Let's say initial transients have died down so that the trajectory is on the attractor, and this is one of my trajectories, xt, and I have another nearby trajectory over here where this is a small separation vector, uh, and its initial length is, let's say, delta 0 is something like 10 to the power of minus 15. This is the magnitude of this vector. So I start two trajectories very close to each other. This distance is, so this was xt, this was xt plus some delta 0. So the hallmark of motion on the strange attractor is that the trajectory grows exponentially by an exponent given by lambda as a function of time. So the neighboring trajectories go separate exponentially fast. In other words, if I plot log delta as a function of time, it would be something like this, where this is a linear slope equals to lambda given by this guy, and this is a characteristic of the log of the initial separation as a function of time. And two things to know is that the curve is never exactly a straight line. And the reason is that it has wiggles because the strength of exponential direction varies along the attractor. And the second thing is that, see, this is a bounded system. Lorenz system is a bounded system. Everything is happening in this point. So even though two trajectories start, they can't indefinitely spread from each other. They have to come back again because it's a bounded system. So the exponential divergence must stop when the separation is comparable to the diameter of the attractor. Also, the lambda, the Lyapunov exponent, the rate at which the trajectories are going, uh, this is the largest Lyapunov exponent in some sense, and the largest exponent of, so what is happening is that, let's say I have a sphere of initial conditions on the attractor. Now I have an n-dimensional space, and hence I have an n-dimensional sphere of, or sphere or a blob of initial conditions. It's going to get deformed into an ellipsoid, something like an ellipsoid, as my dynamics evolves, and each of the directions represents a rate in each of the directions. How the sphere is deforming gives me a Lyapunov exponent, gives me lambda 1, lambda 2, lambda n. So these lambdas are the characteristic deformation of this sphere, and as time goes, for large times, the largest of them dominates. So what essentially we are calculating through this sort of a thing, through our numerics, for long times integrating it, is the largest Lyapunov exponent. But there are other Lyapunov exponents certainly in the problem. So for large T, the diameter of the ellipsoid is controlled by the largest Lyapunov exponent. And there are interesting things. So this Lyapunov exponent, because it's exponential, that actually kills us. So for example, one can define a time horizon. Time horizon is the time beyond which our predictions break down. So for example, I have at t equals to 0, I have two almost indistinguishable initial conditions, and they eventually diverge, and the moment they grow bigger than our tolerance A, let's say A was our tolerance, when we say, okay, we can predict the system within A as our resolution of the true state, so our prediction fails when the separation becomes greater than A, and the time horizon you can easily show horizon. That comes to be of the order of log A by the initial separation. So that's order of 1 over lambda log A times this thing. And it's really the logarithmic dependence on this guy that actually hurts us. No matter how hard we work to reduce initial measurement error, we can't predict longer than a few multiples of 1 over lambda. So that is the idea. I think we did one of the examples over here. Let's say our tolerance was A is 10 to the power minus 3, and our initial separation was 10 to the power of minus 7. And the question is that how long can we predict the system while remaining within the tolerance? Let's say we make even a more precise calculation, and my initial separation I can predict or get it to be 10 to the power of minus 13. We improve our initial error. So if I calculate the time horizon for these cases, 1 over lambda log 10 to the power minus 3 over log 10 to the power minus 7, that gives me 4 log 10 over, yeah, this is natural log only, 4 log 10 over lambda. And in the second case, the time horizon is 1 over lambda log 3 over log 10 to the power minus 13. That is essentially 10 log 10 over lambda. So no matter even if I made the initial error million times better, I was only able to predict the trajectory be within my tolerance for a time which was this divided by this 2 times longer, which is peanuts as compared to the amount of resources I put in to have this trajectory initial error to be a million times better. So only 2.5 longer for an initial improvement of 10 to the power of 6 in the error. So that's how chaos kills us. So summarizing all this, I can actually define chaos. So this is the definition from Strogatz. Chaos is aperiodic, long-term behavior in a deterministic dynamical system that exhibits sensitive dependence on initial conditions. So what are the characteristics? If I break it down, this is an aperiodic long-term behavior, means trajectories do not settle on fixed points, periodic orbits, quasi-periodic orbits, and you know, they are on some funny attractors. So that's why this is second point is that it is happening in a deterministic system. There was no stochastic or no noisy inputs to the parameters. The irregular behavior was arising due to the system's nonlinearity rather than any stochastic throw of the dice. And third was, of course, the sensitive dependence on initial conditions. And that we did this. They are characterized by the Lyapunov exponents. And of course, very importantly, this is occurring in a bounded space. I mean, even an equation like x dot equals to x is deterministic and shows exponential separation on nearby trajectories, but these solutions fly away to infinity. We are interested, and the richness and the beauty comes when we have a single trajectory or nearby trajectories. They keep twisting, turning, remain bounded, but yet exponentially separate away from each other. So that essentially is the hallmark of chaos. Okay, so I think we are almost done. Just that there's a section in Strogatz defining an attractor and what do we call as a strange attractor. So attractor is, we've already seen several kinds of attractor, is a set to which all neighboring trajectories converge. So the formal definition of the attractor is it's a closed set A with the following properties. A is an invariant set. Any trajectory that starts in A stays in A. Any trajectory that starts in A stays in A. Second property is A attracts an open set of initial conditions. So that means that if a trajectory belongs to U, the open set of initial conditions, then as time goes to infinity, the distance of xt to A goes to 0. And third is that A is minimal. That is to say, there is no proper subset of A that satisfies 1 and 2. So we've seen, fixed points, periodic orbits, quasi-periodic solutions, limit cycles, they all follow into these three properties. And a strange attractor is certainly an attractor with one more property. Is an attractor with all three properties that exhibits sensitive dependence on initial conditions. So this is also a contentious definition because strange attractors, and that's also rightly so, are strange because of their fractal dimension. And this is the geometric property why they are called strange. But then there is this dynamical property which is the sensitive dependence on initial conditions. Yeah, so in other words, we have in the last three lectures summarized the Lorenz system of equations starting from the fixed point at the origin, how it loses stability through a pitchfork bifurcation. Then it has got two fixed points which lose their stability. Finally, the motion is on a strange attractor. We discussed the Lyapunov exponents, predictability, and finally combining all of these, we saw how we define chaos and the basic notions about attractors and strange attractors. Thank you.